Yeah, so thanks everyone. So I'm Matthew. I'm currently based at UAE, but I'm going to be talking to you today about some of my work from my masters at Edinburgh in collaboration with the University of St Andrews, really looking at investigating what exactly did the Deccan volcanism, what was the environmental drivers, and do we see any of that in the deep ocean? Moving on. So, as a lot of us are aware, hypothermal events are natural analogues of abrupt climate change, and studying these events in great detail can actually give us some insights into what some future anthropogenic scenarios might result. You can actually see this here in the Westerhold curve, that some of the magnitudes of temperature increase are comparable to some of these future anthropogenic climate projections. And this is not without saying that one of these earliest events, the Late Maastrichtian Warming Event, which is one of the earliest of these transient warming events, a lot of work has been done in recent years to really constrain the changes in climate just predating the KPG boundary. And this warming event, roughly about a 2-degree warming event, has been shown to occur about 340,000 years prior to the impact, and has been causally linked to the onset of Deccan volcanism. And whereas a lot of the literature has been focusing on the environmental impact of the Chicxulub impact, which is known to be the main driver for the KPG mass extinction, the exact environmental impacts of the preceding Deccan volcanism require further research. So what do we know so far about the impacts of Deccan volcanism? So, looking at deep sea core material from 1262 in the South Atlantic, Barnett and others have shown that the deep sea warming commences during eccentricity minimum, 405 eccentricity minimum, suggesting it was potentially another forcing mechanism. But what we do see rather unusually is that we have this muted negative carbon isotope excursion, which some authors have used to suggest that although we see pronounced warming, we're not actually seeing, we're only seeing maybe a small response to the global carbon cycle at the time. We also see that this late Maastrichtian warming event, hypothermal warming, commences during a decline in the osmium isotope concentration, suggesting a link to volcanism. But when we look at carbonate dissolution records of this interval, we only see variable records. And again, some authors have used this to suggest that we're not actually seeing pronounced deep ocean acidification at the time. Equally, recent carbon cycle modelling studies have also suggested various pulses of the volcanism, Deccan volcanism during this period. However, this has not yet been shown well in existing PCO2 proxy records of this time. So there's an obvious research gap that we thought we could plug by looking at trace element geochemistry and looking in deep sea forams like Nathalides trumpii and Stenzarina bacariformis, which we investigated. So as a lot of us are aware, foraminiferal trace element proxies are excellent tools in allowing us to investigate changes in deep ocean saturation states and ventilation in the geological record, and it's something that we thought we could plug in here and use here. So in this scenario, we could imagine that the onset of Deccan volcanism would be associated with large increases in CO2 concentrations. CO2 would be largely absorbed by the oceans, the largest carbon sink. As a result, dissolved in DIC, or dissolved inorganic carbon, would increase in the deep ocean, and we would also expect to see changes in the carbonate saturation state, declines in carbonate saturation. And this should be hopefully recorded in changing trace element ratios of benthic foraminifera, and also changed in the CCD and ventilation as well with warming and increased CO2. So we test this hypothesis by producing the first sub-precession-resolution benthic trace element records from ODP 1262 in the South Atlantic, and it's tuned to an orbitally tuned age model, so we can compare our data to the other data from other sites. So again, we sample preparation analysis involving traditional foram picking, sample grouping, so we have enough calcium carbonate to run our trace element analyses, in the clean lab, crushing, cleaning, and then we're able to run our samples on the triple-core IPCMS available at the University of St Andrews. And this is what we found. So this is our preliminary data coming out from those samples. And what we see is that we identify that within our Nautiloides benthic forearm data, we're seeing this quite a prolonged interval of high dissolved inorganic carbon or low borate ion concentration. And this is actually supported when we look at comparing boron calcium to cadmium calcium, and both proxies could then be suggested to be responding to changes in deep ocean DIC concentration. We also have evidence of this interval when we look at the lithium, calcium and magnesium calcium concentrations of the same samples. We're seeing this quite prolonged interval of low values, which might be corresponding to changes in the deep water saturation state of 1262 at the time. Because we ran Nautiloides benthic forearms, a lot of work has been done to actually calibrate the changes in boron, calcium and Nautiloides to saturation state. So what we can actually nicely do is convert our benthic forearm boron, calcium values directly into carbonate saturation state values. And when we do this, we can actually see that from the pre-event baseline levels, we see a progressive negative 19.91 micromole per kilogram decline from pre-event values to the peak of the warming, suggesting that a pronounced carbon cycle perturbation did take place and is comparable to some other paleo-acidification events that we have limited data for currently. We can make statements about the validity of our data set. If we look, we can actually see by comparing the Nautiloides and the Stenzarina benthic forearm boron calcium values, there is the preservation of the species offset, which would suggest that the primary acidification signal has not been overprinted by secondary diagenesis. We also see that there's evidence to support a weak negative correlation between our magnesium, calcium and boron calcium within the same samples, suggesting that perhaps that we're not seeing any biasing due to any preferential dissolution of boron-enriched calcite in the forearms. So how about the evidence of the Deccan volcanism as a carbon release trigger for this event? So what we see is when we compare our new carbonate saturation state data against this unusual muted excursion that characterises the Late Maastrichtian Warming Event, what we see is that there's actually this 70,000 year lag between significant changes in bottom water carbonate chemistry and the onset of the muted negative CIE, suggesting that this could support a slow but progressive increase in volcanic outgassing, controlling the changes in carbonate chemistry at this time. Also, when we compare our record of saturation state against the osmium isotope decline, we see that indeed they correspond to a period of intensive outgassing of unradiogenic osmium, again suggesting that our low saturation interval is corresponding to increased pulse of potential volcanism at this period. And if we compare it to that carbon cycle modelling study, we can see that there's actually an influx, if it's to be believed, that these pulses represent modelled pulses of Deccan volcanism. Our low saturation state corresponds to an uptake in those pulses that corresponds to the peak of the warming as well. So how about evidence for deep ocean carbonate dissolution in CCD shoaling? So what previous authors have said is by looking at the calcium carbonate percentage records alone, we have this very variable precession amplified dissolution signal, but no significant lack of calcium carbonate within our cores, which some authors have suggested is evidence against significant ocean acidification. But what we see is if we compare those variable calcium carbonate records to the some of our trace element data, like the lithium calcium here, which has been used in the past to suggest a correlation with the CCD depth, we can actually see that the amplified interval and the moving average shows a decline as well during the sort of low saturation interval, that CCD is shown in the trace element records to have increased with those low values that correspond with the amplified calcium carbonate. And this is ODP 1262's paleo depth about 3,000 metres at this time. Again, this is supported if we look at comparing the calcium carbonate records with magnesium calcium, suggesting there's a dampening in the magnesium calcium during the low carbonate saturation interval, suggesting there could be a corresponding link between the low values of magnesium calcium and the increasing amplified signal within the calcium carbonate, suggesting that changes in saturation state are controlling both of these. And if we compare the amplified records of calcium carbonate decline at 1262 with other records in the Southern Ocean and the U1403 in the North Atlantic, we actually see that there is this variable decline in calcium carbonate that corresponds roughly with the changes observed in saturation state at 1262, with the deepest site, U1403 at paleo depth of 4,000 metres, actually showing the decline earlier than in the deeper site. So what this could suggest is that we're seeing during this time of the muted carbon isotope excursion a period of prolonged shoaling of the lysocline that is reflected in the calcium carbonate records as an amplified dissolution. How about the, so obviously we had a warming, but how do we come out of that? So looking at other trace metal proxies, primarily uranium calcium within Stenzarina, we actually noticed that although there's no correlation between aluminium calcium and uranium calcium, a weak correlation, positive correlation does exist between manganese calcium and uranium calcium. And this could be used to suggest that these proxies are responding to relative changes in deep ocean redox, or perhaps export productivity. And this is kind of supported when we compare the uranium calcium records with our carbon isotope records. And what we actually see is that following the low carbonate saturation interval, following between 66.2 up to the KPG boundary, when we see an increase in carbon isotopes, we actually also see a corresponding increase in uranium calcium. And this could suggest that organic carbon boreal was acting as a significant negative feedback following the peak of warming during the Late Maastrichtian Warming Event. And this is also, when we look at the temperature records of the time, we can see that in fact that the uranium calcium values at 1262 decrease during the onset of the warming, but then recover and increase as the bottom water temperatures decrease, suggesting that there could be increases in ocean ventilation, which is a new idea recently, that during these past warm periods we are actually seeing increases in ocean ventilation, and then following that the cooling is supported by increases in the organic carbon boreal. And this is something that, and this is supported by some evidence of changing deep water masses noted in the North Pacific around this time, that correspond potentially to these changes that we're seeing in the records as well at 1262. So I'd like to finish there and acknowledge everyone that's helped me out in this project, and the Paleoclimate Society for allowing me to talk, and especially Dick Kroon, who was my master supervisor, who was really prominent in pushing this work as well. Thank you very much.